So in formalizing geometric proofs, there's a lot of theorems here that are very formal looking. We'll try to simplify them for ourselves a little bit. This first one, oops, lost it, addition theorem for segments. So we have to translate words into pictures. If B is a point between A and C, between automatically means they're on the same line. But it doesn't have to be right smack dab in the middle. So we're there. Q is on a point between P and R. The other thing they tell us is that AB is the same length as PQ. So we got Q is between P and R. Then they tell us that AB and PQ are the same length. And they tell us that BC and QR are the same length. Okay? Well, what that should tell us is that the whole things are the same length. AC has to be the same length, the whole thing. A yellow plus a blue should equal a yellow plus a blue. I'm just going to call that addition for segments. If you add things that are the same size, you're going to get the same result. So the subtraction one is exactly the same. It's just giving you the whole thing. They're saying the whole things are the same. You know, same sort of stuff. B is between A and C. But this time Q is between P and R. But this time they're telling us, use a thinner one here, that AC, the whole thing is the same size as that whole thing. And then AB and PQ are the same. The result should be that the other two pieces are the same. They do the exact same thing with angles. Okay. If they do an angle here, D is in the interior of angle ABC. This is angle AB. The middle one has to be the vertex. D is in the interior. Then they go through that same thing. We've got angle PQR, and S is in the interior. Okay, so then basically what they're saying is that the A, B, D, and PQS are the same, and we also know that this one's the same as this one. Then the result is that the whole things are the same. Then that whole thing must equal that whole thing. Same thing with the subtraction, just like with the angles. If you know the whole thing and the pieces are the same, the other pieces must be the same. Sounds awfully scary. It's really not. And don't get hung up on this stuff. This is not the most important part of geometry here. Okay. Two equal supplementary angles are right angles. So angles are supplementary if they add up to 180. So in order for them to add up to be 180 and be equal to each other, they have to be 90 each. That's all it's saying. You know, complements of equal angles are equal. If angle 1 and angle 2 are complementary, so let's say one is 40 and one is 50. Okay, if I've got some more angles over here, angle 3 and angle 4, and I know that angle 2 and angle 4 are the same size, oh hey, that's 50. Well, what's going to be complementary to the 50? Well, then this has to be 40, meaning those are the same. You know, if it adds up to 90 with the same thing, then it must be the same thing. Okay, or if they're complementary to the same angle, they have to be the same size. If they're both complementary to a 36-degree angle, they're both going to be 54. Same thing with supplements. If A, B, and C are 3 points on a line, with B between A and C, and they really don't even have to say all that. Between tells me they're on a line. Okay, but they can say that. And B is between. And angle ABD and DBC are adjacent. Remember, adjacent means next to, so they share a side. So basically I need another ray here. Here's D. Then these two angles, I'll call them angle 1 and angle 2, have to be supplementary. They make a straight line. Straight lines are 180 degrees. Supplementary is 180 degrees. Okay. Vertical angles. Vertical is used a little differently in geometry with that word. Vertical angles are formed by two intersecting lines. So I've got 4 angles there now that we can see. I would say angle 1 and angle 3 are vertical angles. Angle 2 and angle 4 are vertical angles. They're the ones across from each other in the intersection. Those are vertical angles, and then 2 and 4 are vertical angles. And vertical angles are equal in measure. So in that same picture, this would tell us angle 1, the measure of angle 1 is the same as the measure of angle 3. The measure of angle 2 is the same as the measure of angle 4. So anytime we have those two intersecting lines, if we know one of those angles, we can easily come up with the rest. If I know that this is a 30-degree angle, then I know this one is 30. And I also know that to make a straight line, I need 180, so that's 150, and this is 150. So once I get that one, I can get the others. Okay, so then we put this in proofs, and I know these look super scary, and actually I really want to go down to the one that has part of the things in here for us. Okay, here it is. Okay, so don't panic about proofs. It'll be okay, alright? So you always start here with, there's got to be a starting point, and that's kind of what we talked about in one of the earlier sections. It's the starting point. You know, C is the midpoint of line segment AE. C is also the midpoint of line segment BD. Okay. That's why do we know that? Because they told us that. That's our starting point. That's the given information. Okay, so we can now what we want to prove. They give us one more piece of given information, is that AE is congruent to BD. All right. So they want us to prove that AC and CD are the same. Now, so different thing, you're going to see different things a little bit different ways. So if C is the midpoint of AE, so here's AE, if C is right smack dab in the middle, it means it cuts it into 2 equal pieces, and those 2 pieces have to be the same. And so notice that's what that next statement is. AC and CE must be the same. And then also, well, C is also the midpoint of BD. Well, that means that these 2 pieces have to be the same if that's a midpoint. And notice that's our next statement. So why do we know this? It has to do with midpoint. Okay, the reason you give has to come from something up previous in the proof. Why? And they're probably just going to say definition of midpoint. Okay, sometimes I like to get more specific than that, but definition of midpoint. That's what a midpoint does. It divides it into 2 pieces that are the same size. Okay, now, whoops, jumped on me. So, you'll see this in some books and not in some. The only difference here is that they're saying congruent things also have equal measure. Congruent means the thing itself is the same size and shape. That no line over the top means equal measure. So you're probably also going to see definition of congruence. Okay, I usually make students in high school write, if 2 things are congruent, then they have equal measure. Now remember, segment addition is piece plus piece equals whole thing. So if we're using segment addition up here, we can do piece plus piece equals whole thing on this. Okay, well, the pieces are AC and CE. I need to back out a little bit here. Let me try that. Oh, that's smaller. So I would say that AC plus CE equals AE. Okay, it's just piece plus piece equals whole thing. Okay, I can do the same thing with the other line segment, with this one. So I can say that BC plus CD equals BD, because that's piece plus piece equals whole thing. Okay? Now, if you're looking at some stuff that we've got here, we should see some matching stuff. Notice this stuff matches that stuff. Okay? AE, in statement 4, we said AE was the same as AC plus CE. So we made that replacement. We also said that BD down here is the same as BC plus CD. So we made that replacement. We're replacing things. We're going to call that substitution. Replacing things that are equivalent. Substitution property of equality. But you're always looking at things up above. Honestly, when I'm going to give you problems where you have the choices, is filling in the choices. Difference between statement 5 and statement 6. This is the same. This is the same. This changed and this changed. Everything else is the same. But if we look up in statement 2, it says here that CE and AC are equivalent. So again, they're interchangeable. It says here that BC and CD are equivalent. So that's another substitution. We made a replacement with something that we thought, that we know from up above is the same size. Okay? Now, this one, sometimes you'll see substitution, or you might see simplify. Okay, you might see simplify. AC plus AC is just 2AC. CD plus CD is 2CD. I'm just doing some simplifying. Some books will call that substitution. You're substituting a fact. Okay? Now, if I just divide both sides by 2, what's my result? My result is AC equals CD. So I've divided both sides by the same number, so that's division. And then all I have to do to make it match this exactly is to say, same way we did up here from 1 to 3, they were congruent, so they have equal measure. Well, if they have equal measure, they're congruent. So again, it's just definition of congruence. Okay, just an example of a proof. There's a few in your book that you can look at that are examples. I want to also look at this one other. I'm trying to get this all in quick here. So another thing you might have here is this type of diagram where we need the missing angle measures. So this is so much nicer than the proofs. So vertical angles are equal. So if this one is 40, this one is also 40. So angle 1 is 40 degrees. Okay? Now, you also know that over here, if this one is 85, then this one is 85. So angle 7 is 85. How do we come up with these other ones? Well, remember, straight lines are 180. So if this is 180, 180 minus 40 is 140, and its vertical angle has to also be 140. So angle 5 and angle 6 are each 140. We can play that same game over here with this angle. This has to be a straight line, so 180 minus 85 is 95. So angle 3 is 95. This one's not labeled, but it would also be 95. Now, if angle 1 plus angle 2 plus angle 3 equals 180, so basically a triangle adds up to 180 degrees. So we've got a 90 and a 45 there, that's 135. Angle 2 is just going to be 180 minus the 135 used up, which is 45. So the measure of angle 2 is 45. Well, if angle 2 is 45, its vertical angle is also 45. Okay? Very quick, sorry to rush through that. I didn't want